In this session I will talk a little bit more about philosophical interpretation to some extent of the Heisenberg uncertainty principle, and then talk a bit more about the properties of wavicles, the so-called famous double slit experiment based on Young 1800s British physicist. He performed a double slit, like you have an obstacle here with two slits in it. So imagine a sort of plate with two vertical slits that light can go through the two slits. So sort of here and here. Young's double slit experiment showed pretty definitively that light, now this is 1800s, remember, 19th century, that light was wave-like, because it showed interference effects. And I'll talk a bit about that. But I'll raise the question, what about wavicles? What about, say, photons or electrons? Do they show the same kind of phenomenon as ordinary light? Pre-photon, pre-Einstein thinking, pre-quantum mechanics. But if you do think of light as photons and electrons as wavicles and so forth, how do they behave? Do they generate interference patterns with double slits? So I'll talk a bit about that. It raises some really interesting questions. This discussion of the wavicle double slit experiment was made famous by Feynman, Dick Feynman, who was one of the great middle 20th century theoretical physicists, American, a rather rough New Yorker mentality. He grew up in New York. So with his Brooklyn accent. Okay. And then I'll start getting more into, I guess, the majority of quantum mechanics, people who do quantum mechanics, they more or less accept the probabilistic interpretation of quantum mechanics. A guy called Max Born, so another Max, Max Planck, Max Born, I guess was a popular name in Germany at the time. So a contemporary, well, a bit younger, of Planck. So he eventually got, rather late in his life, he had to wait decades to get it, but he eventually got a Nobel Prize for interpreting the psi, or the wave function, from Schrödinger, as a kind of amplitude. What's that? An amplitude. An amplitude is something that you square, so you multiply it by itself to give you some physical quantity that then you can measure. So for Born, the psi function he squared and interpreted that squared function. So, I'm just giving you an overview at the moment. So he interpreted that as a probability density function. I'll explain what that means. All right, and that will be the end of lecture 1, first lecture. Sort of an overview, general impression of what quantum mechanics is about. All right. Well, let's go back to the Heisenberg uncertainty principle, this famous principle of quantum mechanics, and ask any type of interpretation sort of question. So when you're trying to measure or look at a particle and you're using light, so you may raise the question, well, does the very act of measurement disturb what it is that you are measuring? By looking at something, do you disturb the state that you're trying to measure? Like, if you make a crude analogy, imagine you're trying to measure the position of feathers lying on the floor. And you, the observer, you walk into the room to measure the position of all these feathers on the floor. Trouble is, outside the door as you walk into the room is a gale. There's a lot of wind blowing, right? So as soon as you open the door to perform your measurement, to walk inside and observe, the wind rearranges the feathers. So So the question is it inevitable that quantum mechanics disturbs what it is it's trying to measure in the very act of measuring? Interesting questions. Now, there are things in quantum mechanics called NDM, which is an acronym for non-disturbance measurements. So you can actually measure things without disturbing them. So that's yet another little branch of interpretation of quantum mechanics, and that's all I'll say on that. I will give many lectures in the future if I can live long enough on the interpretation of quantum mechanics. I mean, I have 6 shelves of books on that topic. It's one of my pet topics, and it's one of the things I'm trying to foster. If I can manage to influence, say, a whole generation of young theoretical physicists, mathematical physicists around the world, mostly the first world, then generating a healthy interest in the interpretation of quantum mechanics is a good thing. And I do notice the more modern textbooks increasingly devote whole chapters or more within the text on interpreting quantum mechanics, because it's becoming increasingly popular and more fashionable, I guess. And that's probably due to the influence of, well, several people. One, my old professor, David Bohm, B-O-H-M, because he found an alternative quantum mechanics with the same results, the same measurement results, but philosophically just totally different. It was determinist for a start, so it threw out the statistics, but it got the same results. And then in the 60s, that was in the 50s, in the 60s, John Bell, B-E-L-L, famous name, he came up with some analysis. He was very interested in the interpretation of quantum mechanics, and he came out with his famous Bell's inequalities. Now, just a minute. Yes, I do. Good. The next time I give a lecture on quantum mechanics, it will be at M1, that's first year master's level. And the textbook I'm using is by Mandel, M-A-N-D-L, Mandel, called, just again, same title, Quantum Mechanics. And here's the textbook. Okay, so if you want to go on in quantum mechanics to first year master's level, that's the text I'll be using, Mandel. Now, in it, now let's see, this edition was written, what is it? What edition is it? 92, copyright 92, right? Well, there's a section in it on Bell's inequalities. So if you follow me in quantum mechanics M1, you will come across Bell's famous inequalities. And why are they famous? Because Bell made a prediction that with non-locality entangled pairs of photons, if they come together, get entangled somehow and then fly apart, and then he made some predictions on such system, entangled or non-local, non-locality, non-local systems, that distinguished. It predicted a difference, an experimentally detectable. It's critical. An experimentally detectable difference between quantum mechanics, the predictions of quantum mechanics, and local, meaning in a region of space very close to what's going on, so hence local, and local hidden variable theories. Hidden variables are just extra variables, extra to what's known in quantum mechanics, which allow you then to predict with certainty. So you're going back to the old Newtonian classical determinism. So these extra variables allow you to predict the outcome of measurements of single quantum systems, single electrons, which, well, jumping ahead a little bit, like which slit, this one or this one, does the electron go through, that kind of thing. So hidden variable theories, HVTs, were designed to do that kind of thing. So then in the 70s and early 80s, experiments were actually done to test between quantum mechanics and local hidden variable theories, and quantum mechanics won. So that generated a huge amount of interest, because it seems to suggest, and here's why it's so controversial, the interpretation of quantum mechanics is not a subject that has been settled, far from it. It's just more controversy than ever. But that experimental outcome of the predictions from John Bell, that there would be an experimentally observable difference between the predictions of quantum mechanics and the predictions of local hidden variable theories, and quantum mechanics won, and that seems to suggest that non-locality or entanglement seems to exist. And in fact, it's the basis, that's the irony, that entanglement phenomenon. In other words, what happens here with one entangled particle in zero time, instantaneously influences what happens over here of a second particle, and the distance between those two entangled particles could be like the diameter of the universe kind of thing. They could be hugely separated. But it doesn't matter, they seem to behave as one system. They're entangled, they're connected somehow. And that's the problem, the somehow. What does that mean? What is entanglement? How do you interpret it? How do you even think about it? Does it imply a revolution in our thinking in physics? Duh. Of course. So interesting stuff. So I'll talk about Bell's work, Bell's inequalities, in M1 course. So stick around. Okay. So the HUP. So is it possible to perform measurements without using quantum systems? Like if some sub-quantum phenomena, sub-quantum systems could be used to perform the measurements, could you then not have Heisenberg uncertainty principle? I mean, it looks as though the HUP is due to the kick, the disturbance that the particle you're trying to observe gets from the observing photon, right? That seems like a fairly obvious interpretation. So you're wondering, is the Heisenberg uncertainty principle, is it just a consequence of how clumsy and how brutish and rough and large scale of our measuring tools, like the kick that the photon gives the particle we're trying to observe, or is it somehow more inherent? Is it intrinsic to phenomena at those tiny scales? Here again is one of these interpretation type questions. So is the Heisenberg uncertainty principle due to the clumsiness of our measurements, the roughness of our measurements?